Hello everyone, my name is Kevin Linnane, and today I have code I want to be demoing for you all. It's a large project about using several different machine learning models to try and predict temperature using greenhouse gas values. Then we use a simulation to try and actually use these models that we've created as a means of data analysis and just presenting data and seeing how well or how different temperature could be given a different greenhouse gas values. And that's what the simulation really helps demonstrate with different rates, different ways that society might increase or decrease the greenhouse gases based on their rates or their levels of how much they're increasing and decreasing each year can actually differentiate the temperatures for the next month, let's say for greenhouse gases, and in turn the temperature should also be different. So today it is beautiful out. You can't see, but it's dark. It's 9. It's morning, and it's a beautiful day, and and let's keep it like that. And that's what this project's about. Just trying to present awareness if there needs to be, or to try and prove it in some sort of sense. So we also have a beautiful picture of clouds on the screen. But without further ado, let's get into the background of this project. So here we have an IPyNub essentially. This is where I had created the code to create the machine learning models. It's very messy, unfortunately. I do need to get around to cleaning it up. But if you look into it, there is no data retrieval. That's in another Python file that I can show later. But here we use the data that we collected. So we have N2O, CH4, SF6, and oh man, I'm blanking on one. CO2, CO2, CH4, NO2, SF6. Those are the 4 that we collected through means of, let's say, NOAA's website, which is a free way of gathering data for greenhouse gases, especially those 4, as well as I did some data retrieval to try and predict or see what countries actually gave out their emissions for us to use. However, that data didn't seem as useful as it was very choppy and very unclear, so I used the NAAs mostly. And then I also have a weather repository from Kaggle, which has longitude, latitude on it, as well as the data from 1780 to current, or sorry, not current, 2012. And we use that from 1960 to 2012 or so to create that machine learning model. Without further ado, let's get into this analysis. I'm going to skim over it to try and just highlight the main points because it is very gross, and there's a lot of copying and pasting of code just to try and get through it. It's the means of getting everything I could. But there's graphs in here I want to demonstrate and show. Not that one. That one is really old. But just to start out, these are the different greenhouse gases. So essentially the aggregation of these greenhouse gases created, I'd do a cumulative sum of it. You can't tell inside of these pictures, but from 1990 typically from 1960 to 1990, I did my own linear or residual squared sort of regression here to try and predict or do some sort of backfill of missing data for these greenhouse gases, because the greenhouse gas data was starting at let's say 1998 to 2001 to 2019. So that's what that data ranged from, and I wanted to really bring it back to 1960 as the prediction start date for maybe let's say more data for more training purposes, as well as I thought it was a good starting point because SF6 had started being manufactured in 1953. I had CO2 data from 1960, and then the other 2 data points plus SF6. SF6 wasn't recorded until 2000, so SF6, CH4, and N2O started recording 2000. So and I just wanted to to push it back to, again, just to get more information. But as you can see, there's an exponential rate essentially with the SO6 after creating that residual model, because again it did start in 1960, and it just goes up and up. It's a very dangerous gas. It's still low, very low in numbers, but it is has a high global warming potential. CH4 is a linear path. If we actually do, I don't have a graph right here, but if we actually do a graphing of when the data actually started in 1751, you can see an exponential rate. But if you just zoom in on 1960 to 2000, what is it, 2014, 2000, I guess the data's up there, 2020, 2019 probably is the end date in my opinion, but then you would actually see the exponential rate of increase of CO2. And then alright, here, sorry, I was looking at CH4, my mind's choppy. CH4 is linear. CO2, it has a little curvature to it, but not so bad as I was saying just a second ago. And N2O, and don't read that, is linear. So then this is just me to try and graph data. These graphs didn't mean a whole lot, it's just data distribution. Then afterwards we do a k-means clustering of those resources through the longitude, latitude that we got through our weather data. And that's really nice because that way we can create a model for every cluster for every month. So it comes out to about 240 models for just about every model that we want to test on. So in this specific project we have AdaBoost, linear regression, Bayes linear regression, decision trees, and an ensemble random forest decision trees as well, with having a decision tree as its background classifier, regression learner. So for each of those, it's 240 times 5 times, that's the amount of machine learning models that were actually trained in this process, because of the fact that I wanted to cluster our machine learning models through longitude, latitude, without having to put longitude, latitude as a feature inside our machine learning training modules. So this is just a little graph showing how the k-means actually clustered that data through all that longitude and latitude. Each of these data points essentially makes 13,000 weather. Let me zoom in a little bit. 13,000 weather data points. Unfortunately, you might see that there are repeats in the colors, and that's just because I couldn't get enough symbols from the simple symbols that they give me. And so continuing on, I do have small graphing of the percent averages increase for each month. It's pretty crazy because weather is very hard to actually predict. It's very choppy. You could say it's almost like stock lines or a sine wave. It just goes up and down, up and down, up and down. It goes to a mean. It goes to essentially to a mean every time for every month, which makes sense because it kind of makes sense, I suppose. There should be factors that increase weather though, but it's hard to tell. We would just average increase. These are just to show that weather is hard to predict. It has its ups and downs. It doesn't really have a linear per se regression to it. So the linear models that we are using are predicted to do worse or very bad given variant data. But continuing on, we create the models that we want to learn. I used MPL for a second, but that I didn't want to use that results as a means to one of our machine learning models. And yeah, so this model, we're essentially just saving all these models. The k-means model we're saving. The 5 other models that we're saving, Bayes, all the linear regressions we're saving. And that's just so that our simulation can pull from that and then use it, input values to try and predict inside of it. So the simulation preparation at the bottom here is just saving those files that we want, and also maybe testing more models that I want. I have a p-value tester to determine exactly how what the p rates probability values are for each of the variables that we're testing for each month. Unfortunately, it made my argument less conclusive because each month had different p-values for each greenhouse gas, so it didn't help per se with the ways I did cluster, but I did want to go with this way just to simulate more of a climatic change for the simulation. So again, it's just a bunch of testing. We have the decision tree testing at the bottom, ensemble learning, add a boost, like I was saying. And yeah, without further ado, let's actually go into the code demonstration. If we go over here to simulation, if you ever do, this is a very extendable project I coded it in a sense that you can really create one file with your own policy and chaos rate. Those rates being different ways in which society would react, or how they'd increase or decrease greenhouse gases. You could say you have a political society, so your policy rate would be very high, meaning greenhouse gases would be low, because that means society cares or something like that. And chaos is just like, hey, the world's going very, very terribly, so greenhouse gases might go up, maybe we're just increasing more. In a similar sense, these rates can also be used to help change, or at least like to capture things such as plants reducing CO2, because each of the like I said, it's very easily extendable. Each greenhouse gas has their own rate, so you can easily modify it for whatever values that you think, or if you're very technical in the biological world, then you know what those types of consumptions could be and how they'd affect the atmospheric emissions or reduce the emissions. So if you know that, then you can definitely modify it to that extent. But I did not know that information. I don't know if I could ever calculate that. But without further ado, let's get into the actual demonstration. So we have several different input parameters. I'm just going to print this README out so that way I can review exactly which ones I want to execute. All output is put into a folder. So whenever you create a simulated demonstration of whatever parameters you'd like, it goes into that folder with the same parameters that you put in, so that way you can easily look at it. If you do execute the same parameterized model, then for the simulation, then it just attacks on a 0, 1, or however many times you've executed it to the output file. So you can just look at the most recent number if that's what you're looking for, because there are a lot of data comparisons you can make throughout the simulation. Hopefully I can highlight it with this demo. So let's see. We do use a shell script here. I can just copy this. So let us execute. Let me make sure actually that this output results file is removed. I want to remove it so that I can just easily show you guys what is being outputted, and then show you the results. Unfortunately, this is on a NFS, so I'm having to download some weird things. Whenever I remove a bunch of files, because I've been removing a whole bunch of files from that's outputted from this, I did a notification in my email all about, hey, your Outlook or your NFS is removing too much. Please stop. So let's just ls that again. There's nothing in that results file. Perfect. So let us execute. We have 3 different types of agents that are created. Those agents, again, are the extendable versions of those different chaos policy rates. So those are in the greenhouse agents folder, and right now it's accurate agent, default agent, and greenhouse control. Hopefully you can see that a little better. I don't know how the resolution is right now, but The test pi is just for, you know, I gotta remove that. I can remove that right now. Ah. That's useless. But yeah, you just put in your own .python file in this folder here with its own rates. Of course, you have to modify some methods. You'd copy those methods from the accurate agent and the classes, whatever, so that way it has the same format for us to use for the simulation. But yeah, the accurate agent. I'll just show you. I'll print out these results. Let's do AdaBoost, the AdaBoost models that we've created, and for each of these agents. So I'm just gonna do that. Default agent. What agent? So default random, and then we have a. Oh no, I can't see because my face is in the way. It's okay. Delete is perfect for that. And then we have, sorry, accurate agent. And if we execute this, we're running through a default agent right now, which essentially is just how our machine learning model fares when it's given regular greenhouse data, greenhouse rates per se, because our simulation refers to the rates that are real. For whenever calculating chaos and policy, it refers to how greenhouse should be, because that was the only way I could possibly think about realizing how to calculate the simulation. So here you can see random output. It's not the most prettiest, but essentially that means it is not in the default Python file or default agent file, I guess you could say. It means that it went to the accurate agent and the random agent, and it's telling us that yes, there's policies during these years when we do these greenhouse rates, and that can definitely affect the it could definitely affect how the greenhouse rates are you know, curved, how they are actually to the, or the predicted ones, or the ones that occur in the simulation are to the actual. We're gonna look through those results to, you know, get that more of a picture than me just saying words and thinking that it makes sense. So right now we are inside the accurate agent of our AdaBoost model. I know I was in the file explorer there, but I like to look at pictures using this. Simulation, some results. So we have the accurate agent. No, we want default agent to start with. Just to represent, this is the CH4 over the years. As you can say, the predicted one, which is the one that was created from the simulation, is the exact same as the actual rates are. So this is essentially just showing how AdaBoost works. If we look at the output from April, this is how the AdaBoost would predict April's weather given a greenhouse rate. It's very, as you can tell, actually pretty good. Yeah. Same, this is August's. It goes up and down just as you would expect. So again, this is just highlighting the AdaBoost machine learning model with different months. It's a very, very strong algorithm, I can say that, because it learns from the mean square error of the previous model that it boosted. So it is very strong. So if we look at the random agent now, which just to represent, see the predicted is now very much lower. This means that the policy rate was high, way higher than any chaos rate, and the greenhouse gases went exceedingly down. Hopefully, let's look at each of the greenhouse gases. So CO2 still went down. A little choppy, has a little curvature to it sometimes. N2O, okay, N2O has some, it's pretty close, just edges off at the end there. And then SF6 is, it follows up to 1990, and then it goes its own separate way in this simulation. So if we look at April again, this is how AdaBoost would predict the weather given those greenhouse gases. It looks like it kind of just goes and reverts to the mean of what the actual would be, which makes sense because AdaBoost does learn on mean square error. So if anything, it should be going to the what it thinks the mean square error would be of what the temperature can be. So just going through, every month is printed out because, again, every month has its own model. Every month has an AdaBoost model that's trained on. But yeah, if we look at now the default, no, I looked at default. Accurate agent is, oh, don't want that one. Accurate agent is pretty similar. Policy rate's a little bit better. It's not, or at least it's better to what you'd think the world would do to change greenhouse gases. It's a little lower. It's politically correct. So greenhouse gases for CH4 went a little bit down compared to what the actual was. For CO2, just a little bit below. And then for N2O, a little bit below. And SF6, again, a little bit below. So again, it's just, for my agents that I created, they had a very similar rate for each, or so at least for this accurate agent, they all had the same rate because I didn't know exactly what, which rates I wanted to highlight, as well as what rates I think would be the most accurate or what I'd want to test. So looking at this accurate agent's April, this is AdaBoost's way of demonstrating what it thinks that those greenhouse gases would do. It's probably pretty similar to what you'd expect the default agent had calculated. We could go side-by-side comparisons. I hope that you download the code and play with it yourself and maybe look at that as well. And maybe even extend this project, you know? Wink, wink. So, what else do I want to highlight in this demonstration? We have different parameters we can use whenever calculating these greenhouse gases. Let me actually remember which ones they were by execute. Alright. I'm the wrong folder. That makes sense. Sorry, I just LS twice, you know. I'm probably not the most, I always do things extra. I don't know why, it doesn't register the first time. Execute sim.sh is what I want. Do the help. So we can give it different, I didn't highlight this, but we can give it different longitude latitudes. So I was testing on Atlanta, 33.64 is the longitude, latitude being 77.34. Sorry, wait, that's not actually right. That I was not testing on that. I can tell you for a fact. If we look back to what I actually wrote, it was negative 83.44. So if we type this in, I can't remember what this longitude latitude is because I have done several different tests just to try and play with it again. It's something that you can really lose track of. That's a negative 70, it's negative 80. This should be Atlanta though. I'm pretty sure it's Atlanta. Tuscaloosa Regional Airport. So it's Tuscaloosa, Alabama. Fantastic. Okay, so we can type in any longitude latitude within the United States. It should be the simulation would work. At least it'd have some sort of because it uses the k-means clustering to try and figure out what label it should obtain for that longitude latitude. So I'll just put in some random values for it, and we will test it out. At least similar to what the United States would be. So let's go 36.55 latitude. Unfortunately, if I wanted to print out what latitude, longitude this be, it would require an API, which is lots of HTTP requests, which I mean, maybe it isn't the worst thing, but I didn't really feel like it was that important to know where, unless you know where. So longitude, we'd want maybe negative 80.55. I don't really know the region of the United States, so I'm just going to go something similar to what I think I've been testing on. If it doesn't work, then it doesn't work. So we can actually give another optional parameter of year. So right now the simulation starts at 1916, ends at 2014. But if we want it to be at 1980, that is a possibility for the start of the simulation. Just to run that real quick, and the way it calculates this is actually it does a compound interest, just a compound cumulative sum. Sorry, not interest. Compound cumulative sum of from 1960 to that date to get an initial greenhouse value for that date, as well as the to change the values that we use as greenhouse rates to be what it should be at that day. Again, it is closely related to how the real world works right now. Otherwise, I don't know how to calculate random greenhouse gas rates. So it might take a little bit while to calculate these new initial values because I used a shell script, and shell script can't do float number values. So when I got to that point inside the shell script, I actually had to use a Python command. So this is a for loop of Python values being passed into it, putting into a shell variable, and then we're changing that shell variable multiple times. So it is done, luckily. So I notice how I didn't give a machine learning model input to this. I believe the default model is a linear model, so now we can demo what that linear model would look like. So we go to I used a default agent, so this is going to look like similar values to what it should be. It's actually Bayes linear model. That is the default one. Oops. So notice it has 1980 as the initial the file name for our results. So we open up the N2O year ping. Open doesn't work, so I'm going to Explorer. That's why I like Explorer. Again, the CO2 is the same, and then this is the Bayes linear regression. Simple as that. I do have the some comparison ping files inside if you download this application, just in case you want to look at the different types of models used. We can look at the mean square error. They are actually in the simulation folder, so you don't have to go into anything else, but if we want to look at the accurate agents mean square error, for each of the models it demonstrates the mean square error for that, as you can tell in this accurate one, which has a lower policy rate, but not that much lower than what the default rate might be. The linear model does absolutely terrible. It keeps going out the mean square error, or it doesn't do absolutely terrible. You can look at the results if you want to see how well it predicted the actual temperature, but it didn't do amazing. The mean square error did go up for the Bayesian, the Bayes linear model, and the linear model. If you want to look at defaults models, you can see that everything does pretty good. They're in a similar range. AdaBoost is a median essentially across the board. It might be lower in June, but it actually is maybe even the middle grounds, you could say, for whenever the actual values are passed in, which is a very interesting note to take. And then the last one is random MSEs, and that just means that, remember those, that very differentiated greenhouse gas simulated rates that we calculated? Well, linear models did not like that. They did not like that at all. So you can play around with this simulation a lot. I can show those results if it's needed. But I think that's something that can be played with. So what else can this simulation do? So we have the year. If we want random greenhouse gas initial values, that will change how the rates are predicted. So if we use the default agent, do a tag of -G, I believe. Oops, I don't want 1980. I don't want to do that calculation. Get me out of here. Get me out of here. So we go 1960. Then it will quickly calculate, and we can go there and explore again because that's quicker than anything else. Unfortunately, I should change the folder name whenever I do a. Right, I do a folder name. So it's got a -1 to it, if you can see. 1960-B-1, and then we go over to CH4 values, and remember this was the default. This was the one that it was originally without the randomness. It changes the is on the same as the actual, but now that we have an initial starting value that is different, we can now have a random line, or not a random line, a line that is. It'll probably have the same features as the actual would be, or at least in this situation. But I forgot where I was going with that. Yeah, it just has the features of whatever the actual would be for at least the default agent. For the other agents, it'll be very different. So if we go back again, what other features do I want to show off? 1960-G. -M is where the model comes into play. We had the betas again last time because I forgot to add a different model. But BLAZ. Sorry. You can choose BLAZ or E so you can blaze past this to use a different model. Essentially, that's the acronym, I suppose. It was kind of random, funnily enough. I was making different arguments, and at some point I realized, oh my god, that's what I spelled. I didn't know I'd make a word out of this, but it happened. And but B is Bayes, L is linear model, A is AdaBoost, Z is tree, E is ensemble, Z is I know a random value because I thought I was passing in arguments differently than what I was, and I haven't changed it since. So again, just giving out another test of a different, this is different longitude right here, 1960, year 1962. Actually, let's go to no, I don't like 2012. This will be like a 2-year calculation or something that occurs. I don't know how well this will look. Hopefully okay. The model is, let's go decision tree. Just a regular decision tree. This calculation might take a little bit, but again, I just wanted to show the variety that this project can do. There are random variables set, so inside when we ever calculate chaos policy rate, we use Gaussian and uniform distribution to calculate the next rate. And that's from a random seed file that is within the simulation folder that I'm in currently. I can highlight it, hold up, random seed value.txt. So that just has 1 in it right now, and it can be changed whenever, and that'll just change how the random generation is created. Notice, so each time whenever something's output of the screen right here, that means it's on its next greenhouse value that it's calculating. So SF6, CH4, CO2, and N2O. Essentially, it's calculating that to 2012 to have at least realistic values for the simulation to start with. And then it can do whatever it wants. So even if we do the random greenhouse initial rate, it'll calculate 2012 and then do a range from to that value that it's calculated times 1.5 greater than that range. So it really could be anything, especially if we put the random seed to something else or give it a random seed. Then it will be very, very different. And that's the cool part about this, the variety that comes from whatever values you want to be testing, whatever values that could happen. So while this still calculates, I want to talk about a little bit what the future holds. There are features that could be added to the simulation. I think it would be very important to have actual climate values for each longitude, latitude, for the learning model to learn. I think that'd be really awesome to have, because then average temperature isn't just on greenhouse gases. It shouldn't be, I know, and that's why I did the clustering more so. But the climate would definitely be a factor, as well as not only way of life types of features that could be added is that you could make your own simulation, like I was discussing earlier. Just add a new agent inside greenhouse agents file, which is right here, and that's all it takes. And also maybe even updating the actual ways that these models are trained on could be upgraded in the future, using maybe a Raspberry Pi to collect data from a web scrape data and use that data for the learning models, because right now again the model goes to 2012 at least for the average temperature calculations, because that's all the data I could use. Or is it 2014? So many years, I don't remember. Anyways, so that calculated a dash z, so linear tree. Let's remember that. Did I mean that? Dash z is right here. So this is that what we expected? Yes, that is what we expected. So this is, I guess, suppose an error on my fault. You can only see the predicted values from 2010 or 2012, I suppose, and that's like you can barely see that little line. I think I should just show the predicted values of the actual as well for that. That is my fault. There should be a pretty simple change as well, so I can fix that real easy. But it's good that I'm seeing this. But then if we look at, this means that the dates, I don't know what this means. It means something's wrong. Unfortunate. I'm assuming that it's because they're very far apart. Yikes. Or wait a second. What was my input? It's 2012. Okay, that I was just saying my dates, like when average temperature started, and that was I think 2012 is the end date. So we don't have actual data to compare to at that moment. So that's why that graph looks empty. The simulation does run. It does calculate its own values, but when presenting those results right there, it has nothing to compare to. So there's an error, and I am. So that is a issue that has to do with just arguments that are being inputted. But however, this can be easily implemented to be changed to calculate further than the average temperature date. So we do 2000. I'm kind of afraid to test this now. To test this year, 2010, because maybe I'm wrong about what my idea is. But Let's see. It could be an easy fix if what I'm thinking is right, but it might not be. In which case, I don't know. I think it's right because I've done other dates from 1960, 1980 to 2000, but never 2012. I have not done 2012. So I've never done 2010 either. So it's gonna break, hopefully. If you break something when everything else works, that's kind of a good issue, right? It's a bug that you can almost pinpoint down to. It's not the biggest issue. But yeah, so again, I was saying how you could implement web scraping to update our models for this. That'd be a good feature. But the real purpose of this project was to see, first of all, I had these machine learning models I was creating already for another class, and I really wanted to actually use it in practice, because otherwise that machine learning model becomes useless in terms of being created. It was just created for maybe analysis and seeing if it can happen, but if it's not used in practicality, then I felt like it was a waste. So I was given the great idea to use the simulation with those machine learning models. A lot of it was just so that we can see analysis with that machine learning model, and I think that's a great perk, especially for such a project which has to do with real world values of greenhouse gases. I think that comparison is really important, because otherwise it'd be very difficult for at least a user to just parse through and see what their changes or how their changes affected the average temperature. Fair warning. No fair warning. I was just gonna say AdaBoost is good. So this simulation is this calculation of going to 2010 is almost done. And it's done. 0 more greenhouse gases to calculate. So this is the second time I'm doing a -c, so it will be different. So it appends a oh no, it's the first time because it's 2010. That's right. So greenhouse gases again, got that little dashed line there. April prediction. See, okay, it works. Don't. The predicted temperature is much lower. Not much lower. Not even that much lower. And this was using a decision trees. Decision trees is known for doing this actually, even though I might get random values. I'm just talking about how decision trees typically work. It gives a variance value to what it was trained on. It'll go to essentially a maximum minimum of what it would expect that the target value to be. And even though this isn't a representation of that in this picture, it is lower, and that's interesting. Maybe very interesting actually. That could mean actually that the calculation that was used inside when generating a new compound value for the initial greenhouse rate for 2010, that means that the Python value that was returned to that shell script I was talking about earlier had a rounding, or it rounded, so that changed the actual value. That could be looked at in the future, but at this moment I don't think it's the biggest issue because we're trying to simulate, so why not simulate? Woo! Very interesting. And that's all I think I really have to show for this project. Again, thanks for watching. Thanks for the crazy year. It was fun. Right now, never mind. Right now, or yeah, I'll say this. Right now, it doesn't exactly work for Linux. When I try to upload it later, hopefully it does. It works on Windows, which is my operating system, and the only thing that's different is whenever I pass in the agent through a slash, The sed script in Linux doesn't understand it when Windows does, which I don't think is something I could change besides maybe putting a dot here, greenhouse gas agents dot default agents, which is like how it decide where the path is, I think, and then I have the sed look for that regular expression, or that, yeah, that pattern, not regular expression. But yeah, thanks for listening. Appreciate it and hope you like the project. Goodbye, everyone, and download my GitHub, Scare93. I'll post a link.